In this lecture, we'll look at a very effective technique in Bayesian machine learning known as Bayesian model averaging. Bayesian model averaging belongs to a class of techniques in machine learning known as ensembles. And in ensembles, we combine models rather than select from a set of models. Ensembles have demonstrated real advantages, and let's look at some of these. They improve accuracy. Generally, ensembles are more accurate than single models. And this is one of these surprising things that we see over and over again, that we look at a model, we try and pick out the best model, but often combining the best model with some of the weaker models turns out to give better accuracy than the best model. They also reduce the variance of the results. By ensembling, we can reduce variance and then, as a result, have greater generalizability in our problem space. They also explicitly account for uncertainty directly in the choice of models, and we'll see this as we set up the notion of Bayesian model averaging. There are problems, however. The ensembles are not the complete answer to all of machine learning. The first and most important problem is interpretability. They're very difficult to interpret. If you combine models, it's very difficult to know what features are really deriving the results that we're seeing. Another problem is that the choice of method for combination is not obvious. We need to combine models in an effective way, and unfortunately, there are ways to combine them that just don't work so well. The method we're going to describe today, however, is one of those methods that has shown really excellent performance in a wide range of problems, and as a result, it provides a good method for combination. Finally, there's the cost to build. Putting things together costs time, and both computationally and for the analyst, and this gets translated as a cost to actually construct the ensemble. Okay, so let's look at this technique that's known as Bayesian model averaging, which, as I say, has proven to be effective across a wide range of problems. We'll set it up by letting y be the target variable, the thing that we're interested in predicting or estimating, script d be the data, mk be the models, where k goes from 1 to m, indicating that we have k possible models, capital K possible models, and the parameters we'll represent by bold theta to indicate we've got a number of parameters in those models. Again, the models can have different numbers of parameters in them. They don't have to be the same across all models. So an average estimate for the target, quite simply, is just taking each of these models and looking at the probability of a particular outcome, y, given that model, and then using our posterior for the model, given the data, as the weighting. So we're weighting each one of the predictions from each one of the models, the y that's predicted from each model sub k, and we're weighting it by the posterior distribution for model k. We, of course, can describe and find the posterior distribution for model k using Bayes' rule, and this is just shown here. We're going to use in the numerator the likelihood of the data given a particular model, the prior for the model, and in the denominator, of course, we have the likelihood of the data or the evidence. And that likelihood of the data we can describe using conditioning. And of course, in this case, we will condition on the parameters theta, and we will use our typical conditioning argument where we will assume that we know theta and then multiply by the density of theta given each of the models and integrate out to get the result that we're looking for, the likelihood of the data given the model. Now, there's a more modern approach to Bayesian model averaging that is used because it doesn't require the computation that the previous approach to Bayesian model averaging that we just described does in order to find those posterior distributions in every case. And in this case, we use WAIC. So we're going to use the information criterion that we talked about last time, as a way to compute the weights. And it's a simple approach. We just look and we find the minimum value of the WAI score, which means this is the best model. Because like AIC, we want WAIC to be low. So we're going to find the smallest one of those. Then we're going to take the difference between that and every other model. And obviously the difference or the best of those will be 0. And we'll call that delta K. So that's the difference between each of the individual models and the best performance that we've seen in any of the models in the sense of WAIC. And then recall that WAIC is just an expression of the divergence, and the divergence is minus twice the log likelihood. So we just convert that back in order to get the weights. Since it's a log likelihood, we take it to the exponents, -2, take it to -1/2. And we, of course, do this in a way that's normalized. So we sum in the denominator over all of those values for the difference, and that makes the weights sum to 1. And then Bayesian model averaging can simply be seen as just replacing the posterior with these information weights that we've derived from WAIC, and that becomes the weighting that we use on each one of the predictions given by each of the models for Y. And this is an approach to Bayesian model averaging that is in recent years seen some increase in use as a way to do the Bayesian model averaging ensemble approach to prediction and estimation.